Thanks a lot for inviting me to deliver a talk here. My talk consists of two parts. The first part is devoted to the braided geometry. By braided geometry, I mean geometry related, a sort of non-commutative geometry, but related to a braiding. I will explain a little bit later what doesn't mean braiding. And the second part is devoted to the following problem. You see, if you take a non-commutative algebra, quantization of commutative algebra. We have a commutative algebra, we passed on your non-commutative algebra depending on a parameter. Here we have the usual differential calculus. Differential calculus consists of differential form algebra, Weyl algebra, constructed from the elements of A and the derivations, partial derivative, for example. And what is quantization here? What is analog of this algebra here? What is analog of this algebra here? I want to get here algebras which are deformations of this one. So it is not so evident, because you know, if you want to develop a differential calculus on non-commutative algebra, you get normally algebra which differ drastically from classical one, even if this algebra is taken as commutative one. This is the second part of my communication. So, finally, I will deal here with the commutative algebra, which is nothing but symmetric algebra of GLN. After quantization, I get here algebra, enveloping algebra of GLN, depending on parameter h, which means that I introduce this parameter in the bracket. And finally, I construct a differential calculus on it is an U-type non-commutative algebra.
But the reflection equation is nothing but the algebra.
Reflection equation is special sort of non-commutative algebra related to a braiding. Okay. So I will explain a little bit.
Exactly, quantization of the
there are two
algebra, yes. L plus L minus minus 1.
For example, it is a way to construct this algebra. I will present this algebra in another way. Okay, so what is braiding? Braiding, it is solution of Young-Baxter equation. It is presented on the previous page here. It is well known here in Eller Institute, so I can skip the explication. So now I will consider three types of symmetries. Symmetries involutive. It is called involutive symmetry if braidings satisfy with a relation. I call it Hecke symmetry if the relation is as follows. It is just the Hecke condition. Q is assumed to be generic. And there is another type which is called Birman-Vermitz-Murakami symmetries, just symmetries coming from quantum groups of BCD series. We are interested in the second type, Hecke symmetry. I will explain why the property of Hecke symmetries is better than the properties of Birman-Murakami-Weyl ones. Now, here I present only two examples of Hecke symmetry. It is just Hecke symmetry corresponding to the quantum group UQSL2. It is a similar example, but here quantum supergroup UQ11, and you see if Q is equal to 1, we have just this usual flip. It is deformation of the usual flip. Here we have a deformation of super flip. But the natural question arises whether all Hecke symmetries are deformation or usual flip or super flip. It is not so. Finally, I have constructed 30 years ago many examples of solutions which are not deformation solutions. So in order to study Hecke symmetries, we consider corresponding symmetric algebra on the space V, symmetric in the sense of with Braided, and skew-symmetric algebra. What does that mean? It means that we consider the free tensor algebra quotiented by the ideal generated by the image of the bracket. You see the expression here is just one factor coming in the Hecke relation. Here, just expression second factor coming in the Hecke relation. And we consider the corresponding Poincare-Gilbert series introduced in the natural way. I shown the following relation 25 years ago. It is just classical relation. If it is just usual flip or super flip, it was generalized by myself to the any Hecke relation. Now, the following theorem is very, very strong and very, very interesting for me, but it is not my theorem. The Hilbert-Poincare series is a rational function. It is not evident at all. It is a very difficult theorem. Here, coefficient A and B are positive integer, and polynomials numerator and denominator are coprime. We suppose they are coprime, and all number x, y, and y are real positive. If Hecke symmetry is Q-invertible, I will explain a little bit later what does it mean, then these polynomials are reciprocal. Recently, I have shown with my colleague Pavel Saponov that in the latter case, the polynomial satisfies the mounting properties. Mounting property means that coefficient go up after the middle go down.
How do you prove that the eigenvalues are real and positive?
How to prove what?
That the numbers xi and yj are real positive. How do one can prove it?
Finally, I said it is not my...
No, I know, but still, this is the question. Is it difficult to prove?
For me, it is difficult. I don't know details of this proof.
Well, this looks like wild conjecture somehow. Correct? That's interesting.
I can give you a reference if you want.
Who is author then?
Who is the author?
Vietnamese mathematician Phun Ho Hai and his student.
Okay. This looks like wild conjectures, right? Well.
Okay, now we consider two integers, m and n. It is just the degree of numerator and denominator of this Poincare series. So with couple, with pair, it's just an L of superdimension. You know that in super situation, we have dimension of even part, dimension of odd part. We have two numbers. It is just an L of m. I call this couple B rank of R. If this situation we call the big R braiding even, in this situation we call it odd. In general, if we have the following situation, we have a family of Hecke symmetry depending on parameter Q, and which is deformation of the usual flipper. I state that for generic Q, Poincare series are stable. So if we have a deformational situation, we have the same Poincare series. Poincare series doesn't change for generic Q, of course. But finally, many years ago, I have constructed an example as follows. Finally, you see in the classical situation with degree here equals dimension here. So if we have here 3, the degree of this polynomial is 3 as well. But I constructed example where we can have here 100 any integer here, positive integer of course, and here degree is 2. So by using this example, it's possible to construct a big family of examples which are not not deformation of the usual flip or superflip. Now,
Temporary leap case.
temporal leap, yes, it corresponds to temporal leap, you are right. Finally, now, if we have a transposition braiding R acting in the space V squared, in the same space, it's possible to extend R to the any tensor power of M, so of V. So we can consider this space and extend R to transposition of the space of this type. In principle, it's possible to take a large category which contains some subspaces denoted with lambda. Lambda is a Young tableau, not tableau, diagram. Yes. Finally, it is partition of a number. Finally, we have here category which contains all objects of this type. But now the following problem arises. This category is not for the moment rigid. Rigid means that with any object I should take as my category the dual object. And whether it's possible to include in my category dual object. It is possible to do if our braiding is skew invertible. Skew invertible means that there exists an extension of this braiding R so that we can construct extension on the dual space. So we can apply extended R to V dual squared and so on. And as well we can transpose V and V dual so that there exists a pairing between the two spaces so that this pairing is invariant. This property means that if we take three elements, three objects, and we apply first the pairing here. After that, we transpose U as the first position. Or second way is the following. First, we transpose U here, and after that, we apply pairing on this position. We have the same result for any U, UV or V dual. It is not true that this way of extending exists for any Hecke symmetry. It is not true. For example, if you take as identity operator, it is not possible to extend by respecting this property. If it is possible, our Hecke symmetry is called skew invertible. But general situation is skew invertible. So it is very important property. I learned this property from Lubashenko from Kiev, finally many years ago. But this property is not well known. Finally, it is very important for me because by using this property, I will construct reflection equation algebra. Now, why this property is important? Because if we have this situation, we can consider endomorphism of the space V. It is nothing but the tensor product on V in V star. And we can extend initial R to endomorphisms. So endomorphism is nothing but V tensor product V star. We should transpose with V star, and so it's possible because we have skew invertible situation. Now, I introduced many years ago a generalization of Lie bracket. What is Lie bracket of two elements of endomorphisms? It is nothing but the usual product. After that, we apply this transposition to two elements of the endomorphisms, and the product as well here. It is not difficult to present, to write down all axioms of with generalized Lie bracket. But I would like to stress that it is possible, and this construction is reasonable only if R is involutive. If R is not involutive, this construction is not reasonable because I don't know how it's possible to write down an L of Jacobi identity, and so on, and so on, and so on. And now I will present how it's possible to generalize this construction if R is not involutive. But before, I would like to mention that in 19th, Deligne introduced a notion, Lie algebra in symmetric category. It is just the same. A month ago, I sent a message to Deligne by saying that it is more or less the same construction, but I have no still answer from Deligne. But doesn't matter. Now I want to pass to non-involutive case. In non-involutive situation, now I assume R to be Hecke symmetry. I want to introduce the so-called reflection equation algebra. Reflection equation was introduced by Cherednik with parameter, of course, but this term reflection equation algebra was introduced here, if I am not mistaken, by Petr Petrovich. You know, other algebra is ATT algebra. You see that the relations are not the same, but the both algebras are particular cases of quantum matrix algebras. And
I prefer to call one algebra and another deformed algebra and deformed Lie group. That will be, because the second thing is function of the group, and the first is deformation of Lie algebra.
Finally, my viewpoint is a little bit different, because I would like to say that finally we have algebra on the group GLM, and it's possible to deform with functional algebra in two different directions. The first direction, if we quantize it, we get ATT algebra. It's possible to deform this algebra in another direction, and we have reflection equation algebra. There exists a family of quantum matrix algebra which look like that or that, but it is more difficult to construct them. But I consider the both as a deformation of the same usual algebra. But I will explain a little bit later what is different between them. So my first part of communication is devoted of comparative analysis of these two algebra. I will explain. So now I want to present an example. I consider the simplest example of dimension 2. So my matrix L is generated by 4 elements, and we have the following relations here. Finally, what is problem here? The problem here is it's necessary to show that if we consider the relation presented before, we have just a good deformation of the usual algebra. Good deformation means that Poincaré Gilbert series is classical for generic Q. It is not evident because it's necessary to show it. Finally, the situation is as follows. If we consider a family depending on parameter Q, and for Q equal 1, we have a involutive transposition, involutive symmetry. I state that for generic Q, involutive symmetry, which is not classical, not super classical. So for generic Q, Poincaré Gilbert series is stable. It is not just deformation of the usual flip. It is more general situation. Okay, but now, if we replace in reflection equation algebra the Braided R, Hecke symmetry R by Biermann-Wenzel symmetry, what finally we have? We have a good algebra which is called also reflection equation algebra, but the difference is very important. This deformation is not flat. It means that Poincaré series is not stable. Yeah, and from a deformation point of view, Heike case is more interesting. Okay, but if we apply to reflection equation algebra the following change of basis, we have the following quadratic linear relations. And with quadratic linear relations became just enveloping algebra if Q goes to 1. If we consider Heike symmetry, which is deformation of the usual flipper, in this situation, it is just deformation of the enveloping algebra. You see that we have here a quadratic linear relation. And finally, we have the following situation. We have two-parameter deformation. We have commutative algebra, which is nothing but symmetric algebra of GLN. We have deformation in H. Deformation, it is enveloping algebra of GLN H here. We have a deformation here, which is just a reflection equation algebra. And if we deform in two directions simultaneously, we have modified reflection equation algebra. I call this algebra modified reflection algebra in spite of the fact, but with algebra it is the same. We get this algebra after the change of the basis.
The two parameters Q and H bar have nothing to do with each other.
What?
Q and H bar in this form.
Yes.
They are totally independent?
Independent. For this reason, if we consider Poisson and L-Howitz, we have Poisson pencil. Because you see, we have in this direction one Poisson bracket, in this direction other Poisson bracket, linear Poisson bracket, and they are compatible. So the following problem, I would like to mention the following problem. What is the result of quantization? What is compatibility, condition of compatibility of two associative relations? Nothing. For me, nothing. Finally, we have to construct a new multiplication by quantizing a Poisson pencil so that it depends on two parameters. That's all. That's all. If this quantization is good, it is a quantization indeed. Nothing to do more. Okay, now, what is difference between properties of two algebra? You know well that ATT algebra is Hopf algebra, but it is not Hopf if we have no antipode. It is, I will use the term bi-algebra. And here we have a group-like element, which is called determinant. And in reflection equation algebra, the coproduct exists as well, but we have here braided by algebra. This structure was discovered by Majita. You see on the generator, the coproduct is the same. Coproduct applied to generator of ATT algebra is as follows. Over K. And in reflection equation algebra, it is similar. L here, L here. The formula is similar. But if we want to extend this structure on any element of our algebra, it's necessary to use compatibility of coproduct to product. In this algebra, this compatibility is in sense of Hopf algebra, bi-algebra, and here braided Hopf algebra. It is not the same.
Maybe it's only in your generators, because once more, if I begin with L plus L minus, then the coproduct is simple.
Okay. It's possible to get it by using construction L plus L minus. It's possible, but it is possible. It's possible to use it only in deformational situation coming from quantum group. I present here a picture which is larger. Okay. Moreover, you see that finally reflection equation algebra generated by element L, it is more or less element of the following type. So this element belongs to V, this element belongs to V dual. For T, for RTT algebra, it is not possible to present element in the same way. I would like to say that reflection equation algebra is in sense an object of category mentioned before. Reflection equation, RTT algebra is not. So it's possible to do that span of LEG, generator of reflection equation algebra, is more or less V tensor product V star. And for RTT algebra, it is not possible to present that. What is difference? For reflection equation algebra, there exists a pairing which is invariant. So there exists a pairing between any element of any generators of my algebra. For RTT algebra, it is not possible.
It was Lie algebra, but there's like Casimirs, and in group algebra there is no Casimirs. That's it.
As you wish. So existence of Casimir, it is due to this factor, of course, of course, of course. So what is tracer? On the reflection equation algebra. In this example, the simplest example, trace is given by the following formula. It looks like the classical one, but A and D are weighted. But if you take my examples, the construction of trace exists, but it is more complicated. And finally, we can get here a very, very complicated formula. Okay. Finally, now you see that in Lie algebra, coproduct on the generator is as follows. But if we consider modified reflection equation algebra, which is reflection equation algebra with the changed base, coproduct becomes as follows. In this situation, you see that if Q goes to 1, we have just a similar coproduct. It is.
Once more, I said it's Lie algebra. I don't know what
Yes.
you
Okay.
what you want. There are two dual objects, Lie group and Lie algebra, and they're dual. There is pairing, and arithmetic is it's pairing after quantization. Either functions or differential operators. Acting for differential operator on the function at 0 is pairing.
You're right. Reflection equation algebra is considered often as an Eloho vector fields in quantum situation, of course. It is similar for any situation, not only coming from quantum group, in my example as well. So it is more general, but it is the same. Finally, now, I would like to say the following. In reflection equation algebra, there exists Cayley-Hamilton identity. Two parameters here, Q and H, it is more or less as follows in this example. But in general situation, Cayley-Hamilton identity becomes more difficult. Finally, for the first time, if I am not mistaken, it was considered by Vitaly and Nazarov. But I would like to mention here also Cayley-Hamilton identity by Gelfand and all, because in Gelfand approach, Cayley-Hamilton identity contains coefficients which are matrices. So you see here we have an element from algebra here as well. All coefficients are central. In Gelfand situation, it is not so. For finally, here we have a matrix as well, diagonal matrix. It is not too restricted for Cayley-Hamilton identity. But if you consider general situation, here PI is Berenko. We have the following formula. Here S lambda is sure polynomial. Finally, it doesn't matter. The formula is not so easy. But by chance, it's possible. The formula factorizes itself on two factors. The factors here corresponds to roots which are even. Is the second factor corresponds to roots which are odd. So it is not by force. It is not done by force, but it factorizes by itself this formula. And Now I want to introduce an element which belongs to algebraic extension of the center of reflection equation algebra. So the sum of two roots is just the first coefficient, the product is just the last coefficient as usual. And we will see a little bit later that the difference to roots is very important in this sequel. Now, I would like to pass to differential calculus in the sense of Voronovich. What is calculus of Voronovich? Finally, Voronovich considered the algebra on GLN, and by quantizing that, he considered the RTT algebra. Vector fields, as we discussed just now, it is nothing but reflection equation algebra. But what we did, we considered here modified reflection equation algebra. Here we replaced with algebra by modified reflection equation algebra as well. And finally, after that, we passed to the limit q goes to 1. And we constructed differential calculus. It is differential calculus in this situation, which looks like Voronovich 1. But finally, we have here modified reflection equation algebra, and here modified reflection equation algebra. And finally, we get the following calculus. It is calculus on the group on enveloping algebra of GL2H. So we have, I present here only example. So we have algebra generated by four generator, ABCD. I prefer to pass to quantum compact form, namely this algebra. So we have free generator which form SU2, and T is central. But what are partial derivatives?
It's the same algebra then. It's just, let me see, x equals z, z x, just SL2.
SU2, because it is compact form. SL2 as you wish, it is SL2. Oh, okay, but finally we have a simple part, T is central. It's nothing more. Что?
Другое исчисление хочешь ввести там?
Okay, so here nothing but with algebra. But now it's possible by using passing to this limit to construct differential calculus on this algebra. So you see partial derivative over in T. Commute with T in the following way. If H bar goes to 0, we have classical calculus here. But it is calculus, it is not just calculus, it is Weyl algebra, because here I present commutator because between partial derivative and generators of my algebras. But now, by using the usual approach, by using co-unit, it's possible to compute action of any partial derivative, for example, in x to the product, for example, of yz. So how it's possible to do? You know well that it's necessary by using my permutation relation to put partial derivative from other side. And finally, to apply co-unit. And we get that partial derivative in x applied to yz, it is not 0. It is with result. It's very strange.
What is physical interpretation?
Physical interpretation, so what do you mean by physical interpretation? Okay, we will discuss a little bit later, because physical interpretation here is very difficult. I want only to stress now the differential in one variable in question mark applied to product iz, it is not 0. And finally,
So Leibniz is not true.
Leibniz is not true. Leibniz is deformed. And now I present Leibniz. What is Leibniz? Now I want to apply partial derivative, it is partial derivative, to product of three elements. So we have, we apply d to the first element, d to the second, d to the third. Three terms here are classical. Here, three terms are classical. But now, in this algebra, there exists a matrix product, the usual matrix product. denoted as follows. So after that H, we compute matrix product of two elements, so apply D. It's well defined because it is nothing but coupling. The same here. After that, we compute product of three elements, and here the coefficient A squared. So you see, it is not the usual Leibniz rule. If you want to construct differential calculus by preserving the by common Leibniz rule, it is not possible to construct algebra which would be deformation of the usual differential calculus. With Leibniz rule, it is possible. Okay, so you see very strange differential calculus. If we derive in T a function dependent on T, we have, it is not differential operator, it is difference operator. Of course. But it is not difference operator coming from quantum group. Because in quantum group, Q analog of derivative is more or less as follows. F QHX minus Fx over Q minus 1, here x. It is rather multiplicative difference operator, here additive difference operator. You see, even if we apply differential in x to function dependent here in t to function dependent on x, it is not zero. And finally, because of that, calculations became much more difficult. I will explain a little bit later. Finally, it's possible to construct the RAM operator as well. It is very easy because partial derivatives are already introduced. And the usual property is preserved. D squared is equal to 0. So you see, if we apply Leibniz operator, the RAM operator to the product YZ, we have two terms which are classical. It is just two classical terms, but we have one term more which is not classical. Here, I want to mention other approach to constructing differential calculus on non-commutative algebra. You know that usually with properties, the usual Leibniz rule is preserved. But with relation, commutation between elements of the algebra differential is cancelled. Because of that, the algebra became bigger than classical one. It is not deformation situation. In my case, it is. So with calculus, in approach due to Tsigan, Tamarkin, Ginsburg, Kontsevich, Van de Berg, and others, finally, the role of differential form is played by Hochschild homology. But it is not a deformation object as well. So now,
Cyclic homology.
huh?
Cyclic homology also plays.
Okay, cyclic homology, it was suggested by Kohn. Yes. Kohn. It's Sigan maybe as well. Finally, it is not deformation situation. No, not at all. Okay, now, what is quantization in this approach? We have an equation, for example, Klein-Gordon equation defined in the classical way. But now, we treat all operator coming here as operator on non-commutative algebra. And F is an element of non-commutative algebra. Okay, now,
so your notation, U2H. So you say that you deformed it your way and then put Q equals 1. So Q is not here. Only H remains, yeah?
Here, Q is cancelled because I pass to the limit. Q go to 1. So I prefer to deal here.
So you have your own algebra and now, and then calculus.
Yes, because finally for me it's very interesting question. What we have, what type of calculus we have if we preserve two deformation, two parameters. But it is not yet done. It is now calculated by Pavel Saponov. It will be done, I hope, soon. But finally, I deal only with H deformation.
With Pyatov, we have proposed for Q for H, your H0 and Q.
Finally, Pyatov and you were dealing with situation where the algebra of function algebra with RTT algebra. It is not our case. We are dealing with modified reflection equation algebra as well as quantum algebra. And for this, we can consider two-parameter deformation because of this.
Okay.
With RTT algebra, it is not possible two-parameter deformation.
Okay. No, yeah, this I understood. No, but still,
Okay, now you see.
we treated with Pyatov is most interesting because vector fields and,
Yes,
and
yes.
functions. So
Yes.
it's,
Yes.
so,
Much time ago, it was known the only quantum matrix algebra, RTT algebra. It was treated as an analog of quantization of one group. But now I treat in the same way reflection equation algebra. Okay, now I introduce quantum analog of radius and time. Finally, quantum radius as follows, quantum time, and finally, I consider what is a restriction of Laplace operator of the function dependent on the quantum radius. In the classical situation, we have the following classical formula. In the quantum algebra, we have the following. It is derivation in the quantum radius. It is presented by the following difference operator. And restriction of Laplace operator on the function dependent on the quantum radius is as follows. It's similar to this formula.
the same.
Is the same, yes. And you see, for example, differential in x function depending on the quantum time and quantum radius. It is similar to the classical situation, but you see that the time, quantum time, is impacted as well. It's a very, very strange calculus. Now, for the same reason, we apply Laplace operator to the function depending on time and radius, and we have the following formula. Now, we try to apply it with picture to some equation coming from mathematical physics. It is not easy to do, because finally, if we want to consider function depending on factorizable function depending on space variables, and here function depending on t. And now, if we apply to this function, which is product factorizable, our operator, so derivation on the x, y, z impact t and vice versa. So you see that calculation becomes more difficult. Yes, more difficult. But finally, we succeeded only in calculation in situation where potential is of the following form. We tried harmonic oscillator, it's difficult. We didn't succeed in that. But if potential is as follows, it's possible to compute ground energy, and even it is possible to compute deformation correction to ground energy. I'm not sure that this formula is correct, because I received this formula 2 days ago, so it's necessary to check it. But it is not difficult to compute it in this model.
C should be the fine constant structure in this form.
What?
In classical case,
Yes.
the fundamental state is
Yes.
C square, alpha C square, alpha C square.
Yes, yes. So classical situation is known, and so we would like to compute a correction, the first term of correction. But
Correction to the ground state of the hadrogen atom. The C4 terms.
But here, some physical in question mark phenomenon. I don't understand, but here maybe some energy comes without quantum classical analog. So the number of solution of the corresponding equation became bigger. It is not understood. What does it mean physically?
Dark matter.
Doesn't matter. Finally, for the moment, doesn't matter because no reason for that. So now, I would like to treat. So you see, we have, instead of differential operator, difference operator. It's possible to consider restriction of difference operator on a lattice. And finally, maybe we can consider discrete models. We can consider discrete models. For example, if we consider, for example, yes, yes, maybe. Finally, we plan to apply this approach to other models, but for the moment it is not yet done. So I finish with the following picture. We consider Fermat model M lambda of the highest way. We consider the following representation, usual representation. You know that it's factorizable if lambda 1 minus lambda 2 is integer. So now we can compute the value of the corresponding Casimir belonging to our algebra. We have the following value for Casimir. H comes here. And for the radius, we have here also a series of values. So finally, we can restrict our model on the space where radius at time are discrete. And what is physical meaning of that? I know nothing about that. So, by completing my communication, I would like to mention the following. We consider our algebra, which is nothing but enveloping algebra of U2 and the parameter H here, as a deformation, as a new deformation, as you wish, quantization of Minkowski space algebra. You know maybe other deformation quantization of Minkowski space. So Q Minkowski space, finally, in fact, it is nothing but a particular case of reflection equation algebra. Kappa Minkowski space, which was studied by many people, Lukersky, Valera Tolstoy, and so on, and so on, and so on. But our algebra, in some sense, is for us is more interesting because you see that it is SO3 covariant. These algebras are not. And finally, by beginning, we had a non-commutative deformation of Minkowski space algebras, and we get a model which can be restricted on discrete lattice. Many thanks.
Thank you. Any questions, comments, suggestions?
Okay. I would just mention something, a development which is not connected directly with that, but which came recently. There are a number of people studying Galois theory for differential equations and also difference equation. And rather unexpectedly, recently, I mean, people working with me, especially Umemura from Japan and Heiderich from Germany, etc., we discover that there are situations where the Galois group is really a quantum Galois group. But the situation is that our equations are basically Q difference equations, as they were mentioned, but they are treated in a way where the corresponding Galois group is the corresponding quantum group.
Mm-hmm. Well, difference, certainly, in a way, quantization leads to difference equations instead of continuous.
So we have now explicit difference equation, whereas the Galois group, defined in a very general way, is a quantum group.
In particular, in interpretation of quantized algebra, which I try, so reflection equations is one of them, is that it became nearer to group because we have exponents somehow also for Lie algebraic for analysis of the algebraic elements, we have also exponents. So it's both of them are much more group-like as algebra functions as well as. But in this respect, I can never understand what is this Tanaka-Crane duality. I think it's just simple. You know, the algebra acts on the group, and you calculate things in the one, and that's it. That's all this duality. The object, natural object, is what we call Heisenberg double, namely that unification of both of these algebras. So this will be another quantized cotangent bundle of the group.
Other questions or comments or suggestions? No? If not, let's thank the speaker.